Okay, so now what I want to do is I want to go through these 7 situations where you can use your detailed dynamics. So, right, so each of these 7 situations, and those are the only situations where we use detailed dynamics, and I'm going to give you an example for each one of them. So let's start and look at statics. So right, so what's going on with statics is basically you just have an object that's at rest, right? That's the only thing that's going on here. So what I mean by at rest is I mean that v is equal to 0, a, the acceleration, is equal to 0, and then you also have omega is equal to 0, and the angular acceleration is equal to 0. So basically this is saying it's not moving, right? And this is saying it's not rotating. And so mathematically what that means is that the sum of the forces equals to 0 and the sum of the torques equals to 0. So that way this means you have no acceleration, and this means that you have no angular acceleration. And so the situation that you'd want to think about here is a situation where you have, say, some wall here, and then there's a beam, and let's say the beam is pivoted right here, but it's also being held up right there, and maybe there's some block of mass m hanging off here, and so you have all these various, like some force of tension, and then you have some force down like this. There's also some force of tension on this little string down here from that mass, which is equal to the force of gravity, and then you have the center of mass force down there, and so for each of these you'll have a torque, and the torque is going to be equal to r. So r basically is the distance from, let's say we're considering this as our mathematical pivot, it's the distance from that mathematical pivot to wherever the force is being applied, being multiplied by that force, and then sine of theta is the angle between them, right? So we'll always have something like, let's say this is our r, and then we have some force that's like this, right? It's rf, and then we have some angle theta between them. And then mathematically, just if we want to do sine of theta of, we could do this like sine of theta 2, it would be the same, just because we have the sine of theta is actually equal to the sine of 180 degrees minus theta. So that's just a mathematical thing. So you can't really mess up which angle you do when you're trying to calculate the torque like this. So that's kind of nice. And then we also have these 2 other ways of thinking about the torque, and if you want to review those, I'd recommend looking at the lecture, but as long as you have this one definition, rf sine theta, you should be all set. Okay, so that's one situation, and so this is sort of the example that should be in your head, and you probably remember it from class or other problems that we've had. And then the next example, so this is like the first one. So then the second situation where we have detailed dynamics is motion at a constant velocity. And so this is a physical situation where the object has no net force, right? So the sum of the forces is equal to 0. So this is actually the same as for same as statics, right? Except for the physical situation is different. So like the example I think about here would be terminal velocity, where we have like some force of drag, and then we have the force of gravity acting down, right? We have gravity, and then we'd have one of these 2 drag forces. And let me just make sure I don't. Right, and then so we still have forces, but the sum of the forces equal to 0. But the most important thing is that we do have, I'll do this in a different color. We do have some velocity, so we'll do that in that color. Okay, so the mathematical description here is that the velocity is actually equal to a constant. Or another way to say that is that the acceleration is equal to 0. And the kinematic thing to do is say that x is equal to the initial x plus v x times t. So that's because we have this a, right? We sometimes would have an acceleration term, but our acceleration is 0 here, so there's no acceleration term in our kinematics. So that's what our kinematics is for this one. And then the third situation is when we have a constant acceleration. So 3, constant acceleration. So when we have constant acceleration, I would think of a problem where you just have a ball that's in free fall. So this is the sort of the go-to problem for that, free fall. And so, right, so sum of forces is equal to a constant here. And a second actual situation where this, you might see this, is where you have, let's say, ground down here, and you have some block that's actually sliding, and I'm gonna, let's actually get a new blue pen going here. And so let's say that it has some velocity like this, but then we still have a force of friction, of kinetic friction, acting backward. And so in this situation, you're actually going to have an acceleration, a constant acceleration, and a constant frictional force backward. And so, these are the equations that you'd use for that. So that's a second example that you'd see this in. And the mathematical description we have here is basically that the acceleration is equal to a constant, and then we have, these are kinematic equations, right? Kinematics. And if we're thinking about, say, free fall, then we'd have our acceleration in the y direction is equal to minus g, right? Minus 9.81 meters per second squared. And that's constant acceleration. Okay, and then let's get to the fourth one, which is our uniform circular motion. So this is a situation where you're moving in a circle at a constant speed, right? I don't say constant velocity, because if you're moving in a circle, then your direction, right, your speed could be the same, the length of these are the same, but the direction of the velocity changes. And the net inward force is required to keep it moving in a circle, right? So we don't say centripetal force, we just actually identify the force that's keeping something that's moving in a circle, right? So, you could have tension if you say you have a ball on a string that's swinging around. It could be normal force if, let's say, you have a roller coaster and you have something that's going around in a circle, so you have some inward force from that. Then you could also have static friction. This is for example, if you have, put this one over here, you have some road like this, and then you have a car. This is my car, and it's moving around, going around in, along the circular path. So you have some static friction that's keeping it going in that path, assuming it's not skidding or anything like that. And so those are the typical forces you'll see that's keeping something moving in a circle, and we don't call it centripetal force. We just say that we have some centripetal acceleration that's caused by one of those forces. And so the mathematical description we have here is we'll have our we have some angular speed, that's just the change in the angle over time, and we can actually relate our tangential velocity to our angular speed by just multiplying by r. Remember, r is the way that we connect r, right? So this is connect angular and tangential. Right, so by multiplying by that r, we can get to our tangential quantity. And then we can figure out what some later angle is if we look at the initial angle, and we add omega times time, and then apologies for that. And then we also can figure out what our angular frequency and our angular period is if we're given, say, the frequency not in the angular situation. And And then we have our centripetal acceleration. So basically, let's say, we have something swinging on a string and it's going at some velocity v, or, that has a magnitude equal to v. So the speed is v. So our inward acceleration, right? So our, acceleration, like inward, is going to be equal to v squared over r, or that's equivalent to omega squared times r. And you can find the relation from going from here to here. We can just get that by plugging into v equals omega r. And one thing to note is, so can you use, let me just ask you, can you use this situation if you have, can you use if you have our alpha is not equal to 0? So what if it weren't uniform circular motion? So what if, I'm now sort of getting to a non-uniform circular motion, which is going to be our fifth one. And so can you use this acentripetal in that situation? So you can actually say that acentripetal still is equal to v squared over r here, but this is just equal to the radial, right? So when you have non-uniform circular motion, you can also have a tangential, but the inward acceleration is still v squared over r. So you can still use this equation. Just keep in mind that this doesn't give you the total acceleration. To get the a total, you'd have to have both your a radial plus your a tangential. But you can still use it if you don't have uniform circular motion, if you have non-uniform circular motion. So so that's the fifth situation that how to calculate some detailed dynamics. So the situation I would think about here is maybe something like if you have a CD that's spinning in a circle, right? Starting at rest, and then the CD spins around in a circle, and basically has some angular acceleration. And you can figure out, let's say the torque, you can figure out the angular acceleration if you're given the moment of inertia, right? So this is our moment of inertia. And so this equation is sort of like our Newton's second law, but in the angular situation, because torque is sort of like our, this is like our force. The I here is sort of like our m, and the a, and the alpha is like our a. So it's sort of like F equals m, ma there. And our moment of inertia for a single particle, just for one particle that's, let's say, just spinning, on a bar or a string in a circle, we have I equals m r squared, where we have the m of this particle, and then our r is just the distance there. But if we have many particles, we can find the moment of inertia of all of them, right? So if this were if we had instead, I don't know, some mass here, and it's attached to another mass there and another mass there, then you could figure out the I for all of those by just adding up the mr squared for each of those. We did this when we had some problems where we basically had some spool, and then the spool was attached to a mass over here and a mass over here, and so we could find the moment of inertia of the entire thing, right? This thing was spinning around like that. So that was one situation where we saw that. And then the mathematical description is that we have this angular acceleration, which is equal to a constant. And so this is actually the kinematics here. So here are our, these are our kinematics. Kinematics. similar to 3, right? That was where we have constant acceleration. So, you know, you're more familiar with the linear version of these, but you can just use that same intuition and then just go into our angular quantities. And we derived all of these by just converting from Latin to Greek, if you remember that. Okay, and then, so one more was 6 here, is detailed dynamics of general rotation. So here what we did was we basically took our angular velocity, which we called omega, and we made it into a vector, right? And so what that allowed us to do was describe the speed of rotation, which was the magnitude of this omega, right? That was basically the magnitude of this omega, so it's magnitude there. And then we have the axis of rotation, right? So, you know, like for example, this one, here's our axis. And so that was basically, you could look at the direction of the vector, figure out the axis, and then you could also figure out the direction, right? So basically, this vector also tells you, you know, we're pointing in this direction along the axis rather than, you know, that way. So it's not going that way. And then by making our angular velocity into a vector, or basically taking our angular speed and making it angular velocity, then other angular quantities become vectors. So basically torque becomes a vector too, and so we did our right-hand rule to figure out how to take basically R and F and figure out what the torque is there instead of just using RF sine theta. So one really important consequence of all of this is that the angular momentum is equal to I omega, and if you have our torque equal to 0, that implies that L is a constant because of this equation right here, right? So this equation basically says, right, this is again another way of writing our Newton's second law. So before we had one way of writing our Newton's second law, basically F equals ma here, right? So this is one way of writing our Newton's second law for rotation. Another way of writing it is basically, this is sort of like, you know, our force is equal to, like, you know, dp dt. So this is similar to that, but the really important thing about this version of it is that if you have our torque equal to 0, then that means dl dt, right? L is a constant, you know, or another way to say that is dl dt equals 0, right? So basically, that's really important because, as you saw in the lab and in class, if you have, you know, it's like sort of like a ballerina, when you have these weights and then you pull them in, okay, so you're actually doing energy or doing some work on the weights when you pull them inward, but the thing that's conserved, even if your mechanical energy isn't conserved in that situation, your L is constant. So here, L is constant, and so so here in this situation, you have your I going down. That's why this I right here is getting smaller, and then you have your omega increasing. So you know, keep in mind that angular momentum is constant when you don't have a torque, and if you do have a torque, then your angular momentum changes. And then also, we just touched on, I just wanted to write this here because we touched on it, that we could figure out the precession. So this is when we had like a wheel like this that was spinning around, and then it would actually precess in a circle, which is it's hard to write. I put a video of it so you can see it, but it's hard to draw here. But we didn't cover this in great detail. I just wanted to make sure you had it here, you know, in case you want to refer to this in in the future for all your future precession needs. And then the last example is the detailed dynamics of simple harmonic motion. So the physical situation that I'd say to think about here is, well, our typical one is if you have a wall here, and then it's on some, let's say, like ice or something, some slick surface, some spring, and that spring is attached to a mass. And then the spring has some spring constant K. And so basically, the mathematical way of saying this is that it has a linear restoring force, like a spring. So spring isn't the only situation you could see this in. You could also find this approximate behavior if, let's say you're at the bottom of a hill and you're just oscillating back and forth like this. Then you also get some simple harmonic motion. And one of the most important things about simple harmonic motion is that you can describe it as some amplitude A, so this is our amplitude, and then some oscillating function, because the restoring force basically makes you oscillate back and forth here, over here makes you oscillate back and forth, or right here you'll keep oscillating back and forth. And so you can describe it in terms of A cosine theta or A sine theta based on whether or not, so cosine, looks something like this, right? And sine looks something like this. So it's just basically whether or not at, and this is, basically x on this axis and t on this axis, right? T, x. So it's basically whether or not you're at your starting point at t equals 0, whether or not you're at the maximum displacement from equilibrium, or if you're at equilibrium when you start. That's how you decide whether or not to use cosine or sine. And then if you know m and k, the spring constant, and the mass, you can figure out how quickly it's oscillating, right? And then, so you can figure out your omega, and then earlier we had our equation that related omega to the period and the frequency, so you can relate all of those. So those are the 7 ways of where you have detailed dynamics, basically detailed dynamics being situations where you know what's happening at any given time to an object.